Alright, so we're going to talk about reaction stoichiometry. So we're going to talk about the concept of stoichiometry as it pertains to chemical reactions. When you're dealing with stoichiometry calculations, you're having to use a balanced equation, and that is going to enable us to relate the amounts of reactants needed or products produced in certain situations. Of course, our calculations will involve mass to mole conversions, moles to molecules, and some solution molarity calculations as well. So with stoichiometry, first you need to start out with a balanced chemical equation. So we learned how to do that earlier in the chapter. And a chemical reaction is going to provide chemical formulas with identities of reactants and products involved in a chemical change. Coefficients, the numbers in front of the chemical formulas, provide the number of these chemical species. Okay, so the coefficients represent either the number of molecules of the species or it indicates the number of moles of the species. So when we talk about stoichiometry, we're looking at the coefficient in terms of the number of moles that we have for that species. Stoichiometry is basically a quantitative relationship. And so what that means is we're trying to determine how much reactants or products that are either needed or produced. And so if we're trying to synthesize a substance, for example, stoichiometry allows us to determine how much do I need for both reactants in order to make a certain amount of product. That's very important. So, thinking about our general knowledge of stoichiometry, let's we can sort of analyze it based off information we already know. So, for example, most of us have probably made a cake before or made pancakes by scratch, maybe, from scratch. So here's an example of a recipe where we have it's going to make 8 pancakes. In order to make 8 pancakes, I need a cup of pancake mix, 3/4 cup of milk, and 1 egg. Alright, so if I wanted to write the recipe as a chemical equation, in the form of a chemical equation, so on the left-hand side you would see a cup of the pancake mix plus 3/4 of a cup of milk plus an egg would yield 8 pancakes. Alright, so chemistry is very similar in that fact. We're going to have a balanced chemical reaction. It tells us the ratio. Okay, so for every 1 cup of pancake mix, I need 3/4 of a cup of milk. For every 3/4 of a cup of milk, I need 1 egg. For every 1 egg, I produce 8 pancakes. So we can look at the different possible ratios of each item from one to the other. And that's what we're going to do when we look at stoichiometry in terms of these reactions that we're going to use what's called the molar ratio, which is the coefficient in front of the chemical species we refer to as the number of moles for that substance. Alright, so if we wanted to do some math here, okay, I don't need 8 pancakes. I need, say if I needed 24 pancakes, okay, or 2 dozen. So how many eggs would I need? Okay, well, I know for every 8 pancakes, I need 1 egg. So how do I figure that out? So what I do is, if I want 24 pancakes, that's what I write. Okay, this is really over 1, so the 24 is in the numerator part of the fraction, and there's over 1, so 1 would be in the denominator to see basically how these numbers line up. Because that's important. When you're doing the math, you need to know how to multiply these out. Alright, so we're starting out with 24 pancakes. We want to use a conversion factor that will convert pancakes to number of eggs. And so here I can rewrite this chemical formula here, or this recipe technically, as a conversion factor. And so for every 1 egg, I can produce 8 pancakes. Okay, so how did I know to set it up 1 egg over 8 and not 8 over 1? The reason why is because of my units. Okay, when I use unit cancelization, which is what we've been going through this entire time from the beginning of how to cancel out your units, is very important because this process is the same. So I need pancakes at the bottom, that unit at the bottom, in order for the pancakes unit here to cancel out. Okay, and I'm left with the unit for eggs. Alright, so next is just to do the math. 24 times 1, remember this is in the this number is in the numerator and not in the denominator. So 24 times 1 is 24 divided by 8, well, that's 3. And so we have 3 eggs total that we need in order to make 24 pancakes. Okay, the math is the same when we're doing chemistry. Okay, we're starting out with a balanced chemical equation just like we started out with a recipe. Okay, same idea here. Okay, but we're applying it to chemistry now. Alright, so again, we first need a balanced chemical equation. So we need to, sometimes we'll need to know the amount of reactant required to react in order to get a certain amount of product. Sometimes we need to know the amount of reactants for both reactants. Sometimes we need the amount of reactant needed to produce a certain amount of product. So there's all kinds of ways you can look at it from a balanced chemical reaction. You can look at a lot of different possibilities there. So, of course, the coefficients in a balanced equation are used to derive the stoichiometric factors that permit computation of the desired quantity. So it's very important that, first of all, the equation is balanced. Okay, so here we have a balanced chemical equation. We have nitrogen gas and hydrogen gas reacting to yield ammonia, NH3. And notice that this is a balanced reaction. Why is a balanced reaction so important? Well, we're using, again, the coefficients here when we do our math. So that's why it's very important to start out with a balanced equation to begin with. All right, so we notice here that the relationship between ammonia and hydrogen, there's a 2 to 3 relationship. So for every 2 moles of ammonia, I need 3 moles of hydrogen gas. All right, so you can write that. This is referred to as a conversion factor that's derived from the stoichiometric chemical equation. And so there is a relationship there. So you can write out that ratio as a fraction, 2 molecules of ammonia over 3 hydrogen molecules, or you can write it based off moles. Okay, and that's what we're going to use when we talk about stoichiometry. Now, if you need it to be molecules, you can refer to it as molecules, but really, in general, when we're talking about stoichiometry, the coefficients are representing moles. Okay, moles tells us how many particles there are in the sample, right? It's a way of counting how many atoms or molecules you have in the sample. All right, so here we have an example stoichiometric calculation where we have a balanced chemical reaction. We have 2 moles of aluminum reacting with 3 moles of iodine to yield 2 moles of aluminum iodide. All right, so this equation is balanced. We have 2 moles of aluminum on both sides, or 2 atoms of aluminum, if you want to talk about it in terms of atoms. We have 6 atoms of iodine, and we have also 2 times 3, 6 atoms of iodine on the other side. So the chemical equation is balanced. All right, so here's a picture of that chemical reaction. So we see aluminum, and then iodide is added to the aluminum powder, and the product is the aluminum iodide, and you can see that nice purple gas that's produced. All right, so going back to the equation, we're starting out with 0.429 moles of aluminum. They're asking how many moles of iodine do we need if I have 0.429 moles of aluminum. All right, so we're assuming that we want the same amount of both, okay, in order to make aluminum iodide. We don't want any excess of one or the other, so we want just enough iodide to completely react with the aluminum. Okay, so here's a nice picture that shows you the relationship here. So how do I convert moles of aluminum to moles of iodine? So the stoichiometric factor that we're talking about here is a conversion factor we're using from the balanced equation. Okay, so we're starting out with 0.429 moles of aluminum. And so if we go back, we need to know moles of aluminum. So if I look at my balanced chemical equation, and for every 2 moles of aluminum, I need 3 moles of iodine. So for every 2 moles of aluminum here, I need 3 moles of iodine. Look to see how my units have canceled out, and now I have moles of iodine, which is what I want, right? So you could write this stoichiometric factor or conversion factor the other way around if you needed to. If you needed to convert moles of iodine to moles of aluminum, you would just flip it the other way around if we were given iodine. But because we're given aluminum, we have to use the conversion factor this way in order for the units to cancel out. If you didn't do it that way, then you would end up with something squared, and it would just be a little bit, it would not be helpful at all. All right, so let's talk about the math now. So you're going to multiply 0.429 times 3, okay, divide by 2, and then you get the 0.644 moles of iodine. So this is referred to as a mole-to-mole conversion. Okay, it's something that you're converting moles of one chemical species to moles of a different chemical species, and the stoichiometric conversion factor that's used for this would be referred to as the molar ratio. So the molar ratio is derived from the balanced chemical equation, so you can imagine all the possibilities. With just a simple chemical equation, you can write various different conversion factors from this. For example, 2 moles of aluminum yields 2 moles of aluminum iodide. Okay, you could look at that relationship. You could look at what we looked at, aluminum versus iodine, and look at that stoichiometric relationship. You could look at iodine and aluminum iodide. So, 3 different possibilities here. Just be cautious of that, and we'll do more problems that deal with what's referred to as mole-to-mole conversions. If you wanted to look online, there are probably online things you can do. Just look for mole-to-mole conversions under stoichiometry, and you should be able to find some practice problems that will help you out there.